All right, so we've already talked about heat as a flow of energy going from the warm object to the cool object, and we've already done specific heat calculations. So we're going to do these kinds of calculations that we call Q equals Q. All that means is that the heat lost by one object is going to equal the heat gained by the other objects. So when you look at the picture here, like we were talking about earlier with the heat itself, just definition-wise, talking about the heat going from this dark blue into this red because of the temperature difference, it's going to reach a thermal equilibrium. So this part that's at the higher kinetic energy, that's going to have lost some heat. And then this one here, the red, is going to have gained some heat. So the heat lost by the blue water is equal to the heat gained by this red object in here, okay? So when we're doing our problems, we're going to be able to determine the specific heat of unknown objects is based on this idea of Q equals Q. Heat lost is equal to heat gained. So in this particular question, it says that we have a cylinder, a copper cylinder, that has a mass of, so I'm going to keep track of what's what here. We have copper, and it has a mass of 76.8 grams and a specific heat of 0.385 joules per grams degrees Celsius. It's heated to 86.5, so that's our initial temperature of the copper, 86.5 degrees Celsius. And then put in turpentine. So we have some turpentine over here. And it has a mass of 68.7 grams. And it has an initial temperature of 19.5 degrees Celsius. Whenever it tells you that the final temperature is 31.9 degrees, that's the final temperature of both objects because of the heat flow going from the warmer object to the cooler object. And remember, it stops when both are at the same temperature. So there we go. So it's asking us to solve for the specific heat of the turpentine. So we set it up as Q equals Q. That means that the heat lost from the copper is equal to the heat gained from the turpentine. So we can set this up as MC delta T of the copper is equal to MC delta T of the turpentine. So let's solve for the Q of the copper first. We have a mass of 76.8 grams, a specific heat of 0.385, and a temperature change, 31.9 minus 86.5. Now I'm going to make this positive. It comes out as negative 54.6, but I don't want to have a negative number because it'll end up making negative specific heat at the end. So we're just going to make this positive. It's not going to affect our answer. So that means 76.8 times 0.385 times 54.6 is going to equal 1614.4128. I'm not going to worry about sig figs until the very end. Now that's the heat that was lost by the copper, but remember Q equals Q. So this is now the Q of the turpentine as well, okay? Because of Q equals Q. So we can plug this into a second Q equals MC delta T calculation, 28, is equal to our mass of our turpentine now, 68.7 grams. We're solving for its specific heat, and let's calculate that temperature change for the turpentine here, and that's 12.4 degrees Celsius. So we have to divide our heat by our mass and our temperature change to get the specific heat of the turpentine, which is based on 3 sig figs, because everything has 3 sig figs, 1.90 joules per grams degrees Celsius. Now you can set this up as one big long problem if you'd like. I just showed you as 2 different steps because it's a little easier that way to start it off with, but feel free to just plug this all into one big long string if you like, and then just solve for your missing specific heat. All right, so let's take a look at this example here. When we read it, a 25-gram sample of a metal is dropped into 200 grams of water. Let me add a 0.0 here. I don't hate one sig figs. So 0.0. So since it's talking about two samples getting added into each other, we know it's going to be a Q equals Q. So let's keep track of our substances. We've got a metal here, and it has a mass of 25 grams and an initial temperature of 800 degrees Celsius. It's dropped into water that has a mass of 200.0, as I added the 0, that's initially at 30 degrees Celsius. The final temperature of the system is 40.22. Now remember that final temperature is going to be for both objects because heat flows until they're at the same temperature. So which one are we going to be able to solve for first, the metal or the water? It looks like we don't have enough information for either one of those. But remember, knowing that this is water, that tells us that we have a specific heat of 4.184 joules per grams degrees Celsius, because I can look on my reference chart and get that specific heat. So that means I'm going to solve for the heat, the Q of the water first, because that's what I have enough information about. And my specific heat here, and our final temperature, or sorry, our temperature change is going to be 10.22 degrees Celsius. So when we calculate this, 4.184 times 200 times 10.22, our Q of our water is going to equal 8,552.096. Remember, I'm going to do sig figs at the very end. Because this is a Q equals Q problem, because two substances were added into each other and heat was allowed to flow, the heat that was gained from the water was lost from the metal. So that's also the Q of our metal. So we can plug that into a second Q equals MC delta T. I brought a 6 up there. Problem. Now we're going to use the metal mass, 25 grams. We're solving for its specific heat, and we're going to calculate its temperature change. And it's going to be 759.78 degrees Celsius. So I'm going to take my Q, 8,552.096, divided by my temperature change, divided by my mass, so that I can get rounded to 2 sig figs because of my mass, 0.45 joules per grams degrees Celsius. So then I look on my reference chart so I can identify the metal. I look for something that has 0.45 joules per grams degrees Celsius, and I can see that this metal is going to be iron. Okay, so that's how you do Q equals Q problems. And if there's any questions, don't hesitate to reach out. Thanks.